Hi again. This is my video number 3. Yeah. Again, we are still at the introductory phase of the integral equation. So I just introduce you what is the integral equation, what is the classification of the integral equation, um, the definition of integral equation, linear, and so on. And in this lecture, I'll talk on the special kind of integral equation, special kind of kernel of linear integral equation. Okay, so first thing as we call it as separable. So when we talk on kernel, means the k terms in the integral sign. Yeah. So first is the separable or degenerate kernel. Yeah. Separable or degenerate kernel. So a kernel k is of an integral equation is called separable or degenerate if it can be expressed in the following forms, that is as a sum of finite number of terms, each of which is the product of a function of x only and a function of t only. So our k, this is the kernel, it can be written as a function of x only times a function of v only, and summation of all of those. So it also can also be written as that. So the function ui can be regarded as a linear independence. Otherwise, the number of terms in the above can be further reduced. So just to recall, the function is that linear independent if it can be written as the summation of product of constant times that function equal to 0, where ci give you 0. So we have ci should be dot 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 dot, and this is should be c sub n, c and 0. That is typing error there. So for example, this kernel, you can separate this kernel, so it is not difficult to see this. You can factor out t squared, so that give you t squared. Yeah, this give you t squared x squared plus x. So it can be written in that form. So the multiplication of function t only and function of x only, and as well as for this, you can write as ex times et. So this is a function of x only and function of t only. Okay, next the difference kernel. So all this kernel, the integral equation with separable kernel and some others, will be discuss how to solve this equation in the later lecture. Okay, so difference kernel, consider an integral equation in which the kernel k is dependent solely on the difference xt. This should be x minus t. X minus t. This is xt is given as k. Xt is kx minus t, where k is a certain function. So then k is called the difference kernel of the given integral equation. So in this case, we shall define integral equation of convolution types as follows. So this kind of kernel usually occur in the convolution type integral equation. So for example, this is for the Volterra integral equation. So kx minus t ut, this is t, not u. Again, typing error there. And for the Fredholm integral equation, this is Fredholm integral equation. We have kx minus t ut. Okay. So note that this is for the Volterra because we have the upper limit is variable, whereas this is Fredholm integral. The upper limit is a fixed number. So those two integral are called integral equation of convolution types, where kx minus t, again typing error there, is the difference kernel. Okay. So now let's u1 and u2 be two continuous functions defined for x positive then the convolution u1 u2 is denoted by and defined by. So this is the definition of the convolution of two functions u1 u2. So this is the integrate from 0 to x u1 x minus t u2 t, or 0 to x u1 t u2, this is u should be not y, u2 x minus t dt. So this integral we call it as a convolution integral. Okay, so next we define the transpose kernel. So the kernel K is said to be a transpose kernel if K transpose is equal to K. So where KT denote the transpose of K. Okay, so next we define the Hermitian or complex symmetric and symmetric kernel. The complex kernel K of an integral equation is said to be Hermitian or complex symmetric kernel if K conjugate of K is equal to K. Yeah, conjugate of K is equal to K, where the overbar denote those conjugate. If a complex kernel of integral equation is not Hermitian, then it is said to be non-Hermitian kernel. So for example, the kernel K, so let's just let me give this in a bit more detail. So if you have, for example, K x minus 2 equal to x I x minus t, change that in your notes. There's some typing error there, and as well as there, right? So we have, then if we change that, remember that for the complex symmetric kernel, we have K tx is equal to K xt. Notice the difference between this. This is tx and this is xt. Okay, so if you change that to K tx, that will give you I t minus x. If you take the conjugate of t x, that gives you negative I t minus x. You can also write this is I x minus t, which is this is K xt. So we can see from the K conjugate of K is equal to K. So in this case we call it as a symmetric kernel or Hermitian kernel. Okay, other example you can see from these notes. So that's I've given example earlier. So on the other hand, for example, this kernel kxt equal to I x plus t, this is non-Hermitian. The reason is given there in detail. And the real kernel K is said to be symmetric kernel if ktx is equal to kxt. Yeah, ktx is equal to kxt. And obviously it's said otherwise if the K is called non-symmetric kernel. For example, this kernel, you can see kxt, this is a symmetric kernel because if you change the order t and x, that we have t squared x squared plus tx plus 1, see the same. And as well as this t x plus t just equal to t t plus x. So these two symmetric kernel. Whereas for that, if you change the order of K, that gives you sign. So ktx, let me write this down. If kxt is given as sine 2x plus 3t, so ktx, this is sine, so you have 2t plus 3x. Yeah, definitely this is not equal to sine 2x plus 3t, and this is not equal to k x xt. Okay, so in this case this is non-symmetric kernel, as well as this is non-symmetric kernel, because if we change the order of x and t, that gives you t squared x cubed plus 1. So they are different. Okay, next we look at the iterated kernel or iterated function. So if we consider the Freedom integral equation, this is Freedom integral equation of the second kind. You have ux equal to fx lambda integral a to b k ut dt. So we consider those Freedom integral equation of the second kind. Now if we take, so let me write this thing. If we take k1, if you take k1 xt equal to k xt, and kn xt we define as integrate a to b k x s k n minus 1 st dt, I think ds here, ds, okay, for n equal to 2, 2, 3, and so on. So this we call it as a iterated kernel. Yeah, we call it as a iterated kernel. So why? Because having known k1, because given this integral, Freedom integral fx plus lambda integrate a to b k xt ut dt, Freedom integral equation. Of course, for a specific case, k is given, f is given. Alright, so having known k, we choose k1 as a k, then we can find k2 xt using those formula. So we have a to b kxs k1 st dt. I think this should be dt. Yes, yes. Okay, and k2 k3 xt, this is integrate a to b kxs k2 st ds, and so on till kn xt. So this is if k can be written like this, so we call it k as a iterative kernel. Okay, iterative kernel, sorry. And then for the Volterra integral equation, Volterra integral equation, okay, so we have this is Volterra integral equation. So the iterated kernel kn you define as k1 again, k1 as a kt, and kn as a. So the difference between this iterated kernel and that iterated kernel for the Freedom and Volterra, that the integration here, again, this is the typing error again, this should be a, not t. So the upper limit is x for Volterra, whereas the upper limit b fixed for the Freedom integral equation. Then the resolvent kernel or reciprocal kernel, the resolvent kernel or reciprocal kernel. So if you consider this non-singular integral linear integral equation, non-singular linear integral equation, because this is non-singular and then linear. So this is for Freedom integral equation, this is for Volterra integral equation, and let's say the solution of these two Freedom and Volterra integral equation is given as this, equation number 11 and 12. So ux is fx plus lambda and r and everything there, and then for Volterra integral equation, the solution is given as that ux is fx plus lambda a to x gamma xt lambda ft dt. Then this kernel r and gamma are called resolvent kernel or reciprocal kernel of the given integral equation. Yeah. So this is the integral equation, and if the solution can be written as that, so this R and T, you call it as a reciprocal kernel or resolvent kernel. Okay, so I think I stop here for this video. Again, this is the some definition of the kernel that we might use in the future lecture. All right, so I stop here for this video. Thank you.